Hey everyone, I hope everyone's doing well. Welcome to May in Science. Today we're going to be talking about plate tectonics. It's pretty much the start of the next unit that we would be doing. We're going to do a brief overview today. These slides will also be available in the dynamic crust or plate tectonics folder on my website. Alright, so here we go. So plate tectonics is pretty cool. The Earth is essentially split up into these giant, we call them plates. They're like pretty much giant land masses or masses of rock. And if you look at this map, you could see where it is. So these are all the plates. Now, a plate doesn't necessarily have to just be a piece of continent. Like if you could see this plate here, this is North America, like right here. This plate has North America on it, plus like the Atlantic, some of the Atlantic Ocean. So don't think of the plates as just the continent. They're giant pieces of area. Could be ocean and land together. You can see the outlines here. All right. And essentially, these are floating on soft rock underneath it. The rock underneath it is melted and warmer. And it creates like, you could think of like a raft floating down a river. The land would be like the raft, and the river would be the lava underneath the pieces of land. So these plates are moving all different ways. And when they hit into each other or spread out from one another, they create different things on the surface. So they're all moving in random ways. You can see this picture. Another picture of the arrows. The arrows show which way they're moving. Like in this example here, if you look at the arrow right here, this group, one arrow would be the North American plate going this way, and this one, the Pacific plate, the yellow one, is going this way. So these two plates, the brown and the yellow one, are moving towards each other. That's going to create a certain feature. Now, if you go to this one, the arrow shows the North American plate moving this way, and the Eurasian plate is moving this way, so they're separating at that spot, so that's going to make a different feature. So depending on if they're moving towards, moving away, or you could have like this, they're moving past each other, like just scraping the sides of each other, you're going to have a different feature at those spots because of the way it's moving. And this is around all the edges of all the plates. You're going to have one of these features. So this guy, Alfred Wegener, in 1912, was the person that actually figured out that the landmass, the plates were moving, essentially. And there was pretty much 3 or 4 main pieces of evidence that he discovered that proved it. So the first one was all the landforms fit like puzzle pieces. So if you could see in this picture, Africa pretty much fits into South America and North America. It's not perfect, but if you were to put all of them together in a way, he pretty much said that all of the continents used to be linked, and they called it Pangea. So here's a couple like little maps. Computer models have pretty much reverse engineered where the continents were based on how they're moving today to figure out more detailed maps. This is what they think is going to be the Earth in 50 million years-ish. So you could see like a couple things like Greenland's going to make contact up here. California over here is going to sort of break away from the United States a little bit. So things are constantly shifting around. So a little picture, this would take millions and millions of years. But this is essentially what's going on. So you could see they fit together like little jigsaw puzzles, all the continents. The second piece of evidence is that there are matching fossils of plants and dinosaurs and animals at the spots where the continents fit together like jigsaw puzzles. So if you could see like right here has a matching fossil with right there. Right here has a matching fossil with right there. And so on and so forth. So all these pieces of evidence stacked on top of each other makes it really hard to disprove this theory. More matching dinosaur fossils. There's like land animals that live here that are found, and also the same exact land animal that lives there. So if it's a land animal, there's no way it would have been able to cross that ocean. And there were no planes back then or boats. The third piece of evidence is you also have matching rock layers, matching mountains. Essentially, there's a mountain chain that just splits right here. It just stops because there's ocean, and then it continues right there where we think they would be matched. Again, they fit like puzzle pieces, plus they have a mountain range that's now broken in half. That's pretty serious evidence. And the fourth layer, the fourth piece of evidence is that there's glacier scratches found on rocks. You remember those scratch marks that glaciers leave behind from the last unit, in places that are hot. So like Africa has glacier scratch marks on the rock. So that means Africa was probably once cold, which means it had to move because now it's hot. Okay, so that was his evidence. So now let's talk more about what the plates are actually doing. Essentially, there's a lava pool underneath the rocks, and that's moving. It's sort of like a river of lava underneath the land. And the reason it's moving is because convection currents. The hot lava comes up, and then it cools and moves around and then sinks, and you get these giant wheels, essentially. And they're the reason that the lava is moving this way, which drags the plate along with it. If you put a dish in a river, it's going to move down the river. It's the same exact principle. So at the edges of these plate boundaries, you get most of those interactions. Remember I said in the beginning, if the plates are coming together, if they're spreading apart, if they're moving past each other, you're going to get different features. Coincidentally, on these boundaries is where you get your volcanoes and your earthquakes and anything that involves like tectonic plates, essentially, which you're going to see. Mountain ranges, trenches, which are deep holes in the ground. They're all on the plate boundaries for the most part. There are some in the middle. We'll talk about why in a second. So there's a volcano chain northern California over here. Mount St. Helens is up here in Washington, and Oregon has all these mountain chains. That's because there's a giant plate boundary here. This plate here is moving past this plate here. So you get all these volcanoes here. So there's three essentially directions that the plates can move. If it's convergent, that means the plates are both moving towards each other. Think of the word converge. Converge means to come together. Now this is going to bring your own set of features. If the plates are coming towards each other, you're going to get either a mountain chain, a trench, or volcanoes. A trench is a really big hole in the ground underwater. It's like a really deep area. So you can see here, this plate is going towards this plate. When they come together, this one goes underneath it and melts and turns back into lava, and then the lava comes up and makes all these volcanoes. The trench is here. It's a deep hole like right there. Or you can have a mountain range, which is like Mount Everest. You might have heard of it. And these plates are still moving towards each other, which is actually making Mount Everest rise every year. Divergent plate boundaries means the plates are moving away from each other. So you can see the arrows. Divergent means to come apart. And you're going to get different features at this boundary. One thing that's going to happen is if you imagine you're splitting the earth apart at this, the lava is able to come up. So you get these this crack in the seafloor, essentially, where new lava is being formed. And transform boundary is the last one. This is where one plate is moving past the other one. They sort of like scrape into each other when they move past each other. And this is going to be your most common place to get like major earthquakes. So coincidentally, there is a fault, which is what they call this spot between the two plates. There's a fault through California. That's why California gets so many earthquakes. It's called the San Andreas Fault. You might have heard of the movie San Andreas. That's a transform plate boundary. And essentially, this is a real picture of it. One plate's moving this way, the other plate's moving this way. When they scrape against each other, if you try to scrape your hands together and move past each other, you create friction. That's how you warm your hands up when you're cold. That scraping motion between gigantic pieces of rock creates earthquakes. There are these random spots of lava underneath the crust, which is called a hotspot. You could just have volcanoes randomly around the earth because of these giant magma chambers essentially under the ground. So like Hawaii is a good example of that. Hawaii is not on a plate boundary, but there's tons of volcanoes there. That's because it's on a hotspot. It's just a random collection of magma underneath the earth. All right, we're going to do a couple questions. It's going to be based off this map here, so you can see if you figure it out. The first one is, what kind of plate boundary exists at the Aleutian Trench? So we don't know what that is, but we could just use the map. So you find the Aleutian Trench, which is right here. And the plate boundary is what the arrows are doing. So you see how these arrows are moving towards each other right there? So now you just check the key on the bottom. So is it this one? No, those are moving side to side. Is it this one? No, those are moving apart. Is it this one? Yeah, those are moving towards, so that's called convergent. So this would be convergent. All right, you're going to do the next one on your own. You're only going to worry about these three. Is it this one, or this one? Convergent, divergent, or transform, the three we went over. All right. What kind of plate boundary is the Mid-Atlantic Ridge? All right, well, you just got to find the Mid-Atlantic Ridge, which is right here. Look at the arrows and check which one. Is it this one? No. Is it this one? Yes, it's divergent. All right, let's do one more. Let's do the San Andreas Fault. What type of plate boundary is the San Andreas Fault? All right, well, first you find it. It's right here. Look at the two arrows. They're moving past each other. That would be transform. All right. So that's your little overview on plate tectonics. If you have any questions, feel free to email me. And I hope you guys are doing well. All right. I'll see you on the next one. Bye.